Hello class, it's Miss Augustine again. Yesterday we left off with this slide where we were working on completing our worksheet, and I will be posting the answers today. So now we're ready to talk about how much penetration you can get from the different types of radiation. So this slide is showing you that alpha particles are stopped by a piece of paper. Beta particles penetrate paper easily and are stopped by wood. And finally, gamma, which are the most energetic rays, go through both paper and wood and are stopped by concrete. So if you think about it, when people get upset about radiation, obviously different types of radiation are going to have different levels of penetration, and you could see that in the case of nuclear waste, which is high energy radiation, you certainly would want there to be a lot of concrete between you and the radiation. So in nuclear transformations, which is the subject of the worksheet that we did yesterday, those transformations, as we know, change a radioactive element into a lighter element, and often particles and energy as well are given off. So it turns out that the time that it takes for half of the atoms of a particular radioactive sample to decay is defined as the half-life, T1/2. And again, it's different for each element. So every different radioactive element or isotope has a specific amount of time for that half-life to take place. And again, the half-life being defined as the amount of time it takes for half of a given sample to decay. So some half-life examples here. These are from your textbook. So beryllium-11 decays in about 13.8 seconds. Carbon-14, as I said previously when we were talking about isotopes, takes about 5,700 years. Gold-198, about 2.7 days. Potassium-42, about 12.4 hours. And uranium-238, 4.46 times 10 to the 9th. That's roughly 4.5 billion years. So when you're talking in terms of nuclear waste from a reactor, and you're talking about uranium, the reason people get upset, if you think about it, is every amount that you have on hand. So if you have tons on hand, it takes 4.5 billion years for half of it to go away. So obviously it's around for a long time. So now, when you're doing half-lives, it's helpful to set up a table, such as I have here. And typically what you do is you talk about how many half-lives or decays have elapsed. You talk about the fraction of the remaining sample that is left, or you can talk about the percentage remaining of the sample. And sometimes we'll do it for problems, and we'll, in this column, do the actual amount in grams that's left. So here you'll see after one half-life, you have 50% left. After two, half of that, so 25%. After three, 12.5, and so on. So each time a half-life takes place, you're dividing by 2. So another thing to think about is, using this equation, the number of decays that occur is equal to the time elapsed times the half-life amount. So here's a sample problem. Phosphorus-32 has a half-life of 14.3 days. How many grams of phosphorus-32 would remain after 57.2 days if you started with a 4-gram sample? So I'm going to highlight here the time elapsed right here is 57.2 days. The half-life for this sample is, or for this isotope, is 14.3 days, and we're starting with, at T0, 4 grams. So here, what I'm doing is I'm saying the time elapsed, 57.2 days, divided by the half-life, which is 14.3 days, equals 4. So 4 half-life decays have occurred. So 4 half-lives is equivalent to 1/16, or 6.25% of the original amount. So if you take 6.25% of 4 grams, or 0.0625 times 4, you end up with 0.25 grams remaining. Now, I also wanted to show you how to do it using a chart. So you set up a little table with time and amount, and this is like the lab that you did with the bingo chips. So at time 0, we had 4 grams. That was when we had 100%. After one half-life, divide it by 2. After another half-life, divide it by 2 again. After another half-life, divide it by 2 again. And after another half-life, divide it by 2 one more time. So what we're going to do next is we're going to try to work on a radioactive decay half-life worksheet, and that will be the subject of my next video.